Hello, today we're going to talk about linear density and the total mass of a rod. So this is all part of our momentum chapter, and what we're working towards is the center of mass of an object. But the beginning of this is linear density, and I also hope that it helps a little bit with the calculus so that you can see some of the calculus behind this. So if you have at home, grab some Legos. Notice that you really don't need anything more than 2x2 or 2x4 Legos, and hopefully this will make a little bit of sense when we're done here. So when we look at our Legos, I set this up so that I have a block like this that is really 3x4 of them. And that is if I'm going to say that a 2x2 is one block, and I'm going to say that that is one mass. Now, the whole idea of this is we're trying to find out what is the total mass of the rod. What is the total mass of the rod? So whenever I look at that, and if I define this, there are three different ways that I can find that, three different ways. I can look at purely the number of blocks, because I said one block is one mass, and count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, I can count. So this is going to be 12 masses, right? 12 masses. Now, the second way that I could do this is I could think of this in terms of density and say that if this is the linear density, or how dense the rod is at this point, this is the position of the rod. Notice that the density of my rod, so for instance, I'm going to flip this up this way, you would have no idea how dense that rod is. As opposed to a set of Legos like this that we're going to make here in a second, where this end of the rod is going to be more dense than this end of the rod, but you would never be able to see that here. Okay, so when I look at this, I can say that there is a constant linear density on this set of Legos here that is that 3 value, and it goes all the way across to position 4. So if I think through and I want to find what that is, remember that density is nothing more than mass over the distance or the length or some unit of a distance, right? So if I take that density and I multiply it by the length, isn't that going to give me the mass? And whenever we do that, if I take lambda times x on a graph, isn't that nothing more than the area? It's the area of that graph. So if I'm finding the area of this, then I literally can take and say that my total mass is going to be equal to my base times my height, which is going to give me a value that is this looks like box, but it really says base. It's going to be 4 times 3, and lo and behold, I get the exact same value, that this is 12 masses. 12 masses. Now, interestingly enough, we also know something a little bit about calculus we've studied already. When we talk about the area under a curve, isn't the area nothing more than an integral? So it represents an integral. So what I want to do is I want to come up with this equation for the lambda value, or for the line density. And can't I say, or couldn't I say, that because this is constant, if I have this linear equation here, isn't the x change 0 and the constant is 3? So it doesn't matter what x is, whatever x is times 0, that lambda value is always going to be 3. Now, think through that. If I'm going to say the integral, so I have lambda equals m over x, and I can then take and say that if I move my x over to the other side, lambda x is equal to m, then couldn't I integrate both of these, where this will be I'm going to flip-flop these here now. This will be the total mass, total mass will equal the integral of lambda with respect to x. So now I'm going to do the same thing with this. I'm going to take and say that my total mass is equal to the integral of lambda with respect to x. That lambda equation is just 3, so I'm going to have the integral of 3 with respect to x. Now, is this a definite or an indefinite integral? We would say that it definitely goes from 0 to 4, so I'm going to put my 0 and 4 values there. Then I can plug in and integrate this. So remember that that is going to come out to be an x to the 1 times 3. And then I'm going to take that from 0 to 4, which will literally be 3 times 4 minus 3 times 0, which lo and behold gives me the exact same value, 12 masses. So that's one way the third way that we can find what the total mass is based off of that graph. And here in a second, we'll do a second one in which it is a non-uniform linear density rod. And here we go with the second one. What we're going to do in the second one is we're going to talk about a non-uniform linearly dense rod. So as I'm looking at this Lego set like this, you would have no idea, other than the shadows, that this density is changing. Maybe if I point it this way, here we go. So we have no idea that the density is changing. However, whenever I look at it sideways, you can definitely see that this end of the rod is going to be more dense than this end of the rod. So remember, there are three ways that we can find the total mass, because that's the whole thing that we're trying to find in these. Is the first one we're going to literally do is we're going to count them. Literally count how many blocks we have. So remember, we had defined that one 2x2 block is going to be one mass. So I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 18 blocks or 18 masses in this case. The second thing that we're going to do is the second way we can find that total mass is to graph it. So remember, to graph it, we found the area that was in the graph. Now, if you notice, one of the things that threw me off when I was first designing this lab was that I was trying to take my line from the 3 up here, but then I had this extra triangle up here that wasn't filled and all these extra triangles here that weren't filled, and it was throwing off my values. So I realized that I really have to start in the halfway point here and in the halfway point up here. And so if you can picture this as this line is coming up, I drew it a little too high. This half really comes up and fills in this empty spot. This fills in this empty spot, this fills in this empty spot, and this fills in this empty spot. And that gives me a much more accurate view of my value. Now think through this. If I'm going to find the area of these values, then I can break this up into two different distinct shapes. I can break it up into a triangle and a rectangle. And my rectangle, my area is going to be the base times the height. And for the triangle, my area is going to be 1/2 of the base times the height. So if I add those two together, I'm going to have a total area total of the area of the rectangle plus the area of the triangle. So then I'm going to take my base times my height, which will be 4 times 2.5 times 2.5, because remember, we came up that half of a block there. Then for my area of the triangle, I'm going to have half of the base times the height. So my base is going to be 4 again, and my height is going to be what? 6.5 minus 4.5. I'm sorry, 2.5. 6.5 minus 2.5. And when I punch all those numbers into my calculator, 4 times 2.5 is going to give me 10. And half of 4 will be 2. 6.5 times 2.5, or minus 2.5, is going to be 4. 4 times 2 is going to be 8. So I'm going to have 10 plus 8. And oh my goodness, isn't that amazing that it came out to be 18, which is the exact same number that we have up there. Now, moving on, remember that the third way that we can do this is we can do this by calculus. And so in order to do by calculus, we have to know what the line density equation is. So I'm going to take and set up this lambda equals some value times x plus the some value. So remember that this is going to be the slope of our line. This is going to be the y-intercept of our line. Now, that should be fairly easy. We can think through, well, hey, what's the y-intercept? We already said that that's going to be 2.5, right? 2.5 is that. Now, to get the slope, we would have to end up doing either some complicated math or not very complicated, rise over run, and or in this case, we can literally see that it's going up 1 to 1. So 2.5 to 3.5 in 1, 3.5 to 4.5 in 1. So this is literally just going to be 1x is equal to that lambda value. Now, remember that our total mass is equal to the integral of lambda with respect to x. So we can take and put that equation in then, the integral of x plus 2.5 dx, and it is a definite integral from 0 to 4. So now I need to integrate that. Remember that I can more or less distribute the dx and integrate these one at a time. So to integrate the x value, I'm going to raise the power of the x by 1, which will give me x squared, and then divide by the new power. Then the same thing over here, I'm going to raise this x to the 0 by 1, which will give me x, and divide by 1. And then I want to take this and go from 0 to 4. So I'm going to have 1/2 of 4 squared plus 2.5 times 4. And that's all going to be minus because both of those are 0. It's going to be 0. So 4 times 4 is 16, divided by 2 is going to be 8. 4 times a half is going to be 10. And hey, guess what? I'm sure this came as a surprise to you, but we ended up getting the exact same value, 18 masses from that. So I wondered if any of you thought, hey, is there a way to perform this integral on my T84? And yes, there is a way to perform that integral. So what you're going to do, I don't know how well you can see my calculator here, is you're going to push, I'll pull this slightly out of the way so you can see the directions here. You're going to push the math button, math, and then it's number 9. So if you scroll down, it says function integral. And notice that it puts in, let's see if I pull this up closer. Notice that it puts in, my screen doesn't want to focus on it, that it puts in the integral and you're going to plug in the numbers. And where we're going to get those from is it's going to be from this guy right here. So I'm going to put in 0. I'm going to push up and go to 4. And then I'm going to put my equation in. Now to put the x in, I'm going to use the button here that is xt theta n. So x plus 2.5, go over and put the x there. And whenever you do that, notice that it solves to show that the integral is the 18 masses. Next up, we're going to do a non-uniform linear density rod, and we'll see how that goes. Another uniform linear density problem here. So I put my Legos into this shape now. Notice that it has a much more gradual slope. It's the same number of those. And what I want again is I want to find the total mass. So the first way I can do that is I can count the number of blocks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 masses. So I have 18 masses here. The second way I can do that is I can find the area under the graph. So again, I'm going to take and have a half here and a half up here. And then I'm going to have a line that goes through each of those. So notice how it should go up through the halves at the halfway of each of those marks, because then this half will flip up to this one will flip up to this will flip, etc. Okay, so what I can look at then in order to do this is I can say there is going to be a rectangle on the bottom, and it's going to have a base times the height area. Then there's going to be a rectangle on the top. It's going to have a triangle on the top, 1/2 the base times the height. And in order to find that, I can put those together. I probably should have been drawing that down here, but my total area is going to equal the area of the rectangle plus the area of the triangle, right? So the area of the rectangle is going to be the base, which will be 6 times 1/2. The area of the triangle will be 1/2 times the base, so 1/2 times the base, so half times 6, and then times the height, which is going to be 3.5. Is that going to be 3.5? So this is going to be 1, 2, 3, 4.5 minus 1.5. So when I get that, do those values, I'm going to have 6 times 1.5, which gives me 9, and half of 6 is 3 times 3 is 9, and that is also going to give me, surprise, 18 masses for that total mass. Now, remember then we can do calculus where we can say that the total mass is equal to the integral of the line density with respect to the position. So these graphs are the line density. It's how dense it is here. You can picture that this is more dense on this end than it is on this end. And you can see it on this, but remember, most of the time you'll be looking at an object like this and you would have no idea other than the equation that they're going to give you. Okay, so whenever we do that, we are going to have to come up with this lambda value. So lambda is, since this is a uniform linear density, I can take and say it's something times x plus something, which is our y-intercept. So I know my y-intercept is 1/2. And then the slope value I'm going to have to calculate here. And I'm going up by 1/2 and over by 1. So my rise is 1/2, my run is 1, which is going to give me 1/2 for my slope value. So then if I punch that in, the total mass equals the integral of 0.5x plus 1.5 times dx. I'm going to take this integral from 0 to 6. And remember, I can integrate these individually. So I'm going to have a half of x squared, then divided by the 2. So this is really going to end up being 1/4 x squared. And then this is going to be a fifth, 1.5, can't talk today, 1.5 times x, and that's going to be from 0 to 6. And we're going to calculate what those values are. So 1/4 of 6 squared plus 1/2 of 6 plus 0. So this would be our final value, 6, minus our initial value of 0 to see what that gets. So I'm going to take 0.25 times 6 squared plus 1.5 times 6. And hey, guess what? That gives me a total mass of 18 masses. Again, don't forget that you can do this in your calculator. If you do math 9, then you're going to plug in the values that you have from the math 9 here. So I'm going to have 0 to 6. It's going to be 0.5x plus 1.5 with respect to x. And then notice that it gives me the 18 value there. The next thing that we're going to move on to is a uniform linear density one. And in this particular case, we don't have the Legos. We have to work it out ourselves. So again, that's wrong. A uniform rod of 10 meters of length, so I know that my total length is going to be 10, has a density that varies linearly from 2 kilogram meters at one end to 8 kilograms per meter at the other end. What is the total mass of the rod? So when I go to find the total mass, remember, I'm going to have to do the integral of the line density with respect to x. So the first thing I have to figure out is, what is that line density? The lambda is going to be some slope times x plus some y-intercept. Well, we already know, isn't our y-intercept going to be this 2 kilograms per meter, because that's what our beginning value was. Now, to find the slope, that's going to be our change of y over our change in x. Can't we say that our change in y, which is the rise of this, and the density value, wasn't that 8 minus 2 is our change? And our change in our run is going to be from 10 to 0. And so that's going to give us a slope of 6/10 is going to be the value, which is the same as 3/5. So I'm going to say lambda is 3/5 x plus 2. And everything becomes very much the same as what we did over here then. So we're going to plug our values in, equals the integral of 3/5 x plus 2 dx. I'm going to integrate that. So I'm going to get 3/10 x squared plus 2x from 0 to 10, which means I'm going to have 3 divided by 10 times 10 squared plus 10 times 2, which is going to give me a value of 50 kilograms is going to be my total mass in that particular case. So that's how we would run through a uniform rod, and then a uniform density rod, and then uniform linear density, a couple different ways that you can see that. Next up, we're going to do a non-uniform, non-linear dense rod. Okay, lastly, we have a non-uniform, non-linear dense rod. So maybe you could picture it like a baseball bat, where it's heavier on one end, it gets lighter, and then maybe it gets slightly heavy at the tip where they have the little round part at the end of it. Looking at my pen, I'm automatically thinking that's a non-linear dense rod that is non-uniform also. They would not give you this particular style of it, and they probably wouldn't give you this at all anyway. They would give you something more like this on the AP test, but we're going to do this just for the heck of it. So here are the x and y values for this graph. Notice that it's a cubic function because I have two max mins. I have one min over here, I have one max over here, which means it has to be an x cubed function. So remember that in order to find the total mass, I'm going to do the integral of the line density with respect to the position. So the first thing that I have to do is I have to find out, well, what is that equation of the line density? So the way that we're going to do this is we're going to take these values, we're going to put them into the calculator, and the calculator is going to tell us what that equation is. So I'm going to hit the stat button, I'm going to do edit, and then I'm going to put my x and y values in just as I see them here. So 0, 1, 2, 3, 4, 5, and 6. And then, whoops, I missed one of them. Then lastly, 6.081. And then I'm going to come up here and I'm going to say 1.6666 repeating, 6.333 repeating, and then 10, 11.666 repeating, 9.333 repeating, 1, and 0. So that gives me the values then in the calculator. So the next thing that I'm going to do then is I'm going to hit the stat. I'm going to go over to calculate, and I'm going to push 6 because it's a cubic function. So that's going to be my cube value. And then I'm going to come down and I'm going to calculate that value. So notice that it gives me the equation then. It says that y is equal to ax cubed plus bx squared plus cx plus d, which is our constant at the end. And whenever I look at those values, then I can plug my numbers in. And something is not right about those because I can see instantly that my numbers are not what I'm used to. So this should be 2.6666 repeating. And this should be 6 1/3, 10. I should have double checked my numbers here before I went on there. So I think that might be right then. So if I calculate it now, calculate, there we go. That looks a lot more like what I was expecting. Okay, so whenever I look at these values, then I can take my A, my B, my C, and my D and plug those in. So my A value comes out to be a negative 1/3. So I'm going to have a negative 1/3 x cubed. My b value is a positive, and I'm going to just round that to 2x squared. My c value is times 10 to the negative 4th, so compared to the rest of those, I might as well say that's 0. And my d value, if I round it, is going to be 1. And then this problem becomes exactly like all of the other problems that we've done, where it's literally taking and finding the total mass by integrating that value, negative 1/3 x cubed plus 2x squared plus 1 with respect to x. And then I'm going to take this from x is 0 to x is 6.081. A couple different ways you can do that. You can manually integrate this, or you can integrate it using your calculator. If I integrate it manually, remember I'm going to raise this power to 4, divide by 4, and I'm going to have a negative 1/12 there. Then I'm going to manually raise this power to 3, divide by 3, so 2/3. Raise this power by 1. I forgot my d on there. Raise this power by 1, which is just going to be x, and I want to do this from 0 to 6.081. Remember, I don't add a constant on the end because this is a definite integral. So now I'm going to plug my values in. 1/12 times 6.081 to the 4th plus 2/3 times 6.081 cubed plus 6.081, and all of that minus the same thing with the 0 in for all of our x's, which comes out to be 0. When I punch that into my calculator, I should end up with a total mass that is 42.04 masses between that. That's the amount of mass that would be between the range of 0 and 6.081. Now, again, remember that I could do that on my, calculator. If I go to math, 9 it, and I plug in from 0 to 6.081, then I'm going to put in my equation that will be negative 1 divided by 3 x cubed plus 2x squared plus x with respect to x. Now I want to take, and over here I'm going to insert, I'm not sure if my calculator will do this correctly or not, so I'm going to put a parentheses here just to make sure that it includes insert and doesn't put my x cubed in the denominator. And notice that I get a very different answer, so I must have done something wrong with that. So 1/3 of x up, I see what's wrong right away. This should have been 1/3 of x to the 4th. Then this one would have been 2x. No, I was right. It was the x on the end. So 1/3 squared, and this should have been a 1. And notice when I do that correctly, so even I make mistakes on that. But I could tell something was not right because it didn't match. So I have the 4204, which comes out to my answer. Now, again, remember that this won't necessarily be, you won't see something like this. This is just a for fun, a non-uniform, non-linear dense. Hopefully throughout this, you've noticed how the calculus works for the line density. We're going to use this calculus later on whenever we get into center of mass. So it becomes really important. And I hope that the Legos give you a little bit of a visual too of what that actually means and how that's related to the like adding up the areas. It's just the area under that curve or under the line. And then lastly, one of the key ideas is this idea that the mass is the integral of the line density with respect to position. The integral of the line density with respect to position.